Um, this is the last part of the three-part video that I wanted to upload on and drawing a crank rocker using GeoGebra, animating it, then also constructing the velocity and acceleration diagrams, and also animating them. So when I change the crank angle, I should also get a dynamically the velocity and acceleration diagrams change with the appropriate vectors. So what I've done is I've done a little bit of pre-calculation over here. You can see that so in order to construct the acceleration diagram, having done the velocity diagram is out here. So you can see that u represents basically the velocity of point C. So which is this is rotating counterclockwise, so it is pointing in this direction. The purple corresponds to velocity of point D, absolute velocity of point D, and the blue vector basically is the velocity of point D relative to C. So because we use the equation that V of C is or V of D is V of C plus V of D relative to C. So now when we come to the acceleration diagram, we have a similar concept. The acceleration of D is acceleration of C plus acceleration of D relative to C. Now in the acceleration, unlike velocity, there are two components. There is a normal component and a tangential component. So as far as the acceleration of C, the normal component alone is present. The tangential component is not present because we are assuming that it is rotating at a constant angular velocity. The normal component, of course, is going to be omega 2 square times O2C. Remember omega 2, I have assumed it to be 1. So what I have done is I have in this over here, if you see this right here, I have calculated length of u is this vector length divided by h, which is basically the length of O2C. So that gives me omega 2. B, which is length of w, which is the relative velocity component, divided by the length of the coupler, gives me omega 3. So B corresponds to omega 3, and C3 here basically, which is length of V divided by J, gives me the omega 4. So this is the magnitude of omega 4. Now then I have computed the omega square r components. D3 is basically a square h, which simply means that that is the normal component of the acceleration for point C. Then O, which is b square into I, is the normal component of the relative acceleration A of D relative to C. And finally R, which is basically the C3 square J, is going to be the normal component of the acceleration of D. So these three are known. So let's try to put that first in the acceleration diagram. Then the two quantities which are basically unknown will be the angular acceleration associated with point D. So which is the tangential component of AD, and the tangential component of A of D relative to C. We don't know the magnitudes, but we do know the directions associated with this. All right. So let's start the construction. So let's first mark, as we'll start with the link 2. So we know that the angular acceleration for that is basically going to be parallel to O2C. So we draw a line here. From OA we mark that. So the angular acceleration is basically normal component is along this, and it is pointing towards O2. So which means this vector is going to point towards that direction. What is the radius of this? The radius of this is given by this quantity D3, which is a square h. So we draw a circle whose center is going to be at OA, and the radius we make it as D3, D underscore 3. So D3. Okay. So you can see that circle has been done. Then the intersections, or maybe before we do the intersection, let's fill the, probably let's do the intersection, mark the vector, and then proceed towards the other two. All right. So let's look at the intersection between the circle and the parallel line. So that is point G and H. We are not interested in H because it has to point towards O2. So we hide the circle and we hide the line, and now we go back to this arrow mark here so that we can do some editing, reduce the size of this, possibly make it 3 point over here, and we'll rename this D. This happens to be nothing but our C, right? So we'll call that C, and now draw a vector which is going to be going from OA to point C, and we leave it in green color because that is the color of that link that we have. Alright, so now the next thing that we will do is to draw the normal component of the link 4. So you see that that is given by R, which is C3 square times J. Yeah. So again, let's draw a circle. Let's first, of course, it has to be parallel to this, so we'll construct the parallel line. So we take a line which is parallel to DO4, again passing through OA. So again, now we mark a circle whose radius is basically equal to R. Okay, so it's a small circle. Then we'll again look for the intersection of this object and this object. G and I come up since it has to be pointing towards O4. So we remove G and we hide the lines together. So I again, so we go back to the arrow to make the I dot smaller in size so that it's easier for us to, so we make it 4 and 3. Yeah, so and we'll call this since that's going to be the normal component, so we'll call it dn, the point to be dn. Okay, so and then we draw the vector which is going to go from OA to basically dn. So that's drawn. Because let me zoom in a little bit. So you can see this. Let me make the OA also to be a little smaller. Okay, so we have this. Let us change that color because that is part of that. I'm going to use purple to represent all of these components associated with this. We'll change that to a purple color. Alright, and now the other normal acceleration component which is known, but that will start from C because it's a relative acceleration term. So let's look at that. There we are going to have basically a, what was the quantity that we came up with? Let us go up, and it's called O. So over here, first of all, it has to be parallel to this line, blue line. So we draw a line, parallel line first. Draw that parallel line, and it has to be parallel passing through C. And then we mark basically the distance has to be basically O. So we can say compass circle, sorry. So draw that and say that radius is basically O. And again, remember that it has to point towards C. So when we look at the intersections here, this point is what is going to come into the picture, and J will be hidden here. So we are not interested in J. So let's just make sure I've drawn the right circle. O, the radius of O is 0.77. Okay, fine. That's fine. Let's just check. Yeah, that's fine. Okay, all right. So let's hide the circle, let's hide the line. Now we draw a vector which is going to start from C and end at I, and again let's do some make this point to be a little smaller. I'm going to call that, remember that this is the relative T velocity acceleration of D relative to C normal component, so I'm going to call it dCN. Then I'm going to also make that a little smaller, the dot to be a little smaller. So let's make it one more level smaller. So and then the color of this we will carry that to be blue to go with the link color that we have. All right, so fine, so we have that DCN. Now to close this polygon we need to basically use the fact that we know the angular acceleration associated or sorry, the tangential acceleration directions for the ADT as well as A of D relative to C tangential component. So remember that is going to be perpendicular to this, the relative component, so you put that there, so over there. And similarly this is going to be perpendicular to this, and that is going to start from over here. So therefore the intersection of this gives us the point D, and our acceleration polygon construction is complete. So let's go ahead, get the intersection over here and this point and that point I. Again let's go back to the arrow point here, make this I small, call it 4 3 and then that is nothing but our point T. Okay, all right, and now we can remove hide the two perpendicular lines, and now we close the polygon by drawing the appropriate vectors. So I draw the vector. This is the tangential component of AD, and so let's change the color, let's put that back to purple. So this is the tangential component. So if you measure that vector length and divide by O4T, you will get the angular acceleration at that configuration. Similarly, let's close the other part of the vector equation. So let's draw the vector. So here, from here to here, and again let's change the color to reflect that it is part of the relative acceleration term associated with link 3. So here, so that's the polygon that is complete, and so the diagram is complete for this configuration. Now I can kind of change this and see what happens. So let me go ahead, go to this angle. So you can see that as I rotate this point C basically will move on a circle because it's constant angular velocity. So you can see various the size and shape of the acceleration polygon is changing as I move this, right? So you can see now yeah, so let's, and it has changed direction. As you can see, DN is now lining up, and it is becoming bigger. In fact, it is growing, right? All right, so with this I will stop. I hope you have been able to get some understanding of how to do this on your own, and GeoGebra is a nice platform to do this. Okay, all right, thank you.